but it's not like a big star cluster, but we're seeing down to the scales of individual star or multiple stars all the way out 1 billion years after the Big Bang.
Okay, wow. And speaking of, this star being within the first billion years of the Big Bang, Patty, how did astronomers know that about this star? How did they know it was in there?
That's a great question. And so, like many of the images that Hubble takes of these fields, these treasury fields, we're observing them to collect as much data as not only the team wants to get the science that they want to get out, but that the entire community can really mine that rich archive and get a lot of science out. So one of the ways you can get the most science out of an image like this is to observe it in multiple filters. And the filters are basically different colors of light. So they specify a certain range of colors. And so this is a multicolor image using 2 instruments on the telescope. And what that allows us to do is, for the galaxies, each galaxy is going to have a certain brightness in those filters. And we can look at how that brightness changes as a function of our filter. And what we see with these objects that are very far, they're redshifted. We call it redshifted. As they move further from us, the whole universe is actually expanding. The light gets shifted into the red. And what that will do to a galaxy's spectrum that's far redshifted is it'll actually kind of block it out in the optical. You won't see the light there. It'll just start to peak out the redder and redder that filter gets. So if you notice in the image that smear that we're looking at, the sunrise arc it's called, it's very red compared to the rest of the image. And that's why, is the light's just starting to pick up as we go redder. And you can use that to estimate its redshift. And that is exactly how the objects in that arc are estimated. They're all at about the same redshift of 6.2. And you use that number and the photometric information that you have to estimate everything else. Its distance and then its size scale is related to that. So there's just a tremendous amount of scientific information in these multicolor images, in addition to just the beauty of looking at the galaxies that are in them.
Oh, yeah, for sure. And Patty, also, why is it important to be studying this star that is within the first billion years of the Big Bang?
So when we look around at our local universe or the stars in our own galaxy, we get a picture of how the universe has evolved. And one of the coolest stories about that is where matter came from, where the heavy elements came from, where the carbon, calcium, oxygen that makes up everything, our bodies, our bones, our telescopes, where did those elements come from? And the answer is that they're fused in the centers, in the cores of stars. And massive stars in particular are very efficient at this. They fuse lower elements like hydrogen and helium into heavier elements, and then they explode in supernova explosions, and they spew that material out into their local environment so the next generation of stars can pull that in as they're forming. Those are the kind of things that form rocky planets like the Earth, where we've got like an iron core and all those elements in our atmospheres. Those were fused in earlier generations of stars. So Earendel is this single star, the farthest yet that we've been able to observe, and it will allow us to see how that process started to be put together in the very earliest days. When did those very early heavy elements start to be infused into the material? And it's just a window that's opening up onto the next big thing, because that light is pushed so far into the red that we need a telescope that can go even further into the red than Hubble can to really uncover the cool things.
Yeah, and speaking of, I think another fantastic part about all of this is that there's already approved observations to look at Earendel with the recently launched James Webb Space Telescope, which is a super powerful infrared space telescope that just launched in December. We're so excited for it to begin science operations this summer. And Jane, could you kind of tell us how Webb might bring this Hubble discovery even farther?
Sure. So I learned about this lens star when the discoverers came to me, said, so do you want to be, we're trying to figure out how to plan some Webb observations. Are you in? I'm like, oh, I'm totally in. That's cool. So what we worked out was a set of observations with NIRCam, which is the near-infrared imager, to get colors in all of those filters that are too red for Hubble to do well, right, or to do at all, right? And so Webb will pick up where Hubble left off, getting redder filters. So we'll have very crisp, gorgeous images. We've already proven with Webb that we can take gorgeous images. It's as a very, very sharp telescope. And now we're getting the science instruments ready to go. The second science instrument that we will target for this galaxy and star is NIRSpec, the near-infrared spectrograph. And so we'll be taking spectra of not only the lensed galaxy, the sunrise arc, but also the star Earendel. And so the NIRSpec has a lot of cool bells and whistles. One of them is it has this microshutter array that has 250,000